Okay, welcome to the campus of Big Sandy Community College, the Prestonsburg campus. This is the first ever flipped video for AP Calculus. So you're kind of seeing something different here. Part of our flipped unit that we're going to be trying here at AP Calculus. So we're going to start off with our first unit here, so we're limits and continuity. So we want to get right into it, take a look at a little introduction here, a little information first about the unit here. All right, so this is actually Unit 2. We did the trigonometry, that would have been Unit 1, so we're finished with that. We've had our quiz on that. Okay, so this unit involves limits and their properties. It's important to have a good understanding of limits as we move into derivatives and other topics in calculus. So in this unit here, we're going to do a little preview of calculus. How's calculus different from pre-calculus? After that, we're going to move into finding limits graphically and numerically. Now, so, two ways. After this, we're going to take a look at evaluating limits analytically. So we'll be using some of our algebra skills there, some factoring skills to calculate limits analytically. Then after that, we're going to move on to continuity and one-sided limits. So once again, continuity is important when we get into derivatives. So we're going to look at continuity of one-sided limits, and we're going to finish this unit up with infinite limits. So vertical asymptotes, infinite limits should be that difficult. So let's get started with our first video here. So this is a preview of calculus. Now this video is being filmed in July. So like I said, I'm in Prestonsburg at the Big Sandy Community College, so you kind of see me dressing down here. I don't have my tie, so that's okay. So let's get started. A little preview of calculus. A little bit of information about it. Okay, first, calculus is considered to be the mathematics of change, whereas pre-calculus mathematics is stationary. Calculus is dynamic, motion, things are moving, etc. Calculus is considered a limit machine. Okay, if you have a good understanding of pre-calculus mathematics, so you're good at algebra. Okay, you can go from there, you learn limits, and then there we move into different topics of calculus. Now, there are two problems that are key to understanding calculus. Now, these are two concepts that in the old days, back before calculus, these two types of problems used to give mathematicians a lot of problems, a lot of trouble. Okay, one is what's called the tangent line problem, and the area problem, calculating area under a curve. For calculus, that was very difficult to do. And getting finding the slope of a tangent line to a curve was very difficult prior to the development of calculus. So two major problems that calculus, I guess, was developed for: tangent line problem and the area problem. So, and a little bit about some differences between pre-cal mathematics and calculus. Okay, first of all, pre-calculus mathematics, you find the value of x as x approaches c. I'm going to run through these very quickly, just for your own benefit. In calculus, you would find the limit as x approaches c. Right? Now, in pre-calculus, you would find the slope of the line. Right? So we all know how to find the slope of the line. Now, in calculus, you would find the slope of a curve, so the slope of a tangent line to a curve. Right? Now, in pre-calculus, you might find the secant line to a curve. Well, in calculus, you would find the tangent line to a curve. In pre-calculus, you would find the average rate of change. Now, in calculus, we can find the instantaneous rate of change. So the rate of change at a particular moment in time. In pre-calculus, you would find the area of a rectangle. Well, in calculus, you would find the area under a curve. Okay? In pre-calculus, you would find the length of a line segment, okay, the distance formula. In calculus, you would find the length of an arc. Okay? In pre-cal, you would find the surface area of a cylinder. In calculus, you would find the surface area of a solid of revolution. Right? So you would find the volume of a rectangle in pre-cal, geometry. In calculus, you would find the volume of a region under a surface. Right? So you would find the volume is that's not too difficult. It involves integration. Now, two concepts here we want to review real quick. First of all, make sure you remember what a secant line is. Now, I'll do a circle. Here's my circle. Now, a secant line is simply a straight line that intersects a curve at least 2 points. Right? So intersects a graph or a curve at 2 points. Here's my circle, you can see the secant line. As opposed to a tangent line. So let's kind of review this. I'm not for sure if you've ever done much with tangent line before, but a tangent line to a curve would be, now here's my curve. Now a tangent line, okay, touches the curve at 1 point, not 2 points. Right? And as you, in either direction on either side of the curve is going to be equidistant from your curve. So that's your tangent line on a curve. Okay, secant line is going to touch at 2 points, tangent line only 1. So intersect the graph at 1 point. Okay, now let's take a look at what's called the tangent line problem. So this is one of the big concepts of calculus that basically kind of brought about the development of calculus to be able to calculate the tangent line to a curve. Now, what the tangent line problem involves, so here's my curve. Right? Now, what I'm going to do, I'm going to pick out a point. Let's say this point right here. So you can see everything coming in here on our PowerPoint. And you can see this point here at the bottom. In order to get the tangent line to this curve, okay, what we do in calculus, okay, we're going to let this point, this x value down here be c. All right, so when we draw our chord or our secant line here, we're going to come down and we're going to come h distance down here on the x-axis. Right, so this is c, this down here is c plus h. So we're going to come a certain distance away from c, and we get a secant line here. So what's going to happen? Now notice, this is my secant line. Right, so we're going to describe our 2 points. This point right here will be C, f of c. Right? Okay, the other point on the secant line is going to be c plus h, and this would be f of c plus h. That would be your x value, that's your y value. Right? Now, what happens in calculus, okay, we're going to let this distance, h, right, so this distance away from point C, as it gets smaller and smaller. Notice the next secant line here. Okay, now this time, h is getting closer to this x value here. So it's getting closer and closer to c. Now notice the slope of our secant line now is going to get closer to what we would expect the slope of your tangent line to be. So look at our secant line now. Now let's come a little bit closer. Let's let h become a little bit smaller. So as h gets closer to C again, right, you can see the new secant line. Right, so as this distance here gets smaller and smaller, as it gets closer and closer to C, okay, this secant line now is becoming, I guess, closer to what we would expect the slope of the tangent line to be. Okay, now here's another one. So you see we get closer. This is h. So as h gets closer again, and you can see we're almost this secant line is almost our tangent line. The slope of the tangent line and the slope of the secant line, there will be very little difference between the two slopes. And then as you come all the way in, as it gets all the way in, you can see that the slope of the tangent line, it now becomes what is essentially the slope of our tangent line. So we say in calculus now, as h approaches 0, so as this distance here gets smaller and smaller and smaller, and gets closer and closer to c, okay, the slope of the secant line approaches the slope of the tangent line. That's how we would in calculus, that's how we use derivatives to get the slope of that tangent line, and you're actually using the slope of the secant line to do that. So this is the tangent line problem. I said prior to the development of calculus, getting the slope of that tangent line was really pretty difficult. Now let's take a look at the area under a curve. Now, area, this is another major problem, concept from calculus. Let me bring my graph back up here. Now, let's say I need to find the area under a curve from A to B on our curve. So here it goes. So this is my graph is y equals f of x. Right? Now, prior to the development of calculus, area under a curve basically just had to be estimated. Right? You would, and to estimate it, typically you would use some type of geometric shape, maybe a rectangle, possibly a trapezoid. Trapezoids can be used to estimate area under a curve. Prior to the development of calculus, really this area could only be estimated. Now notice, to find the area from A to B, okay, under our curve, I've used 4 rectangles. Now notice with 4 rectangles, you can see these little triangular area between the curve and the rectangle. Okay, that area is missing. So this area if I use 4 rectangles to estimate my area, I would get an underestimation for the actual area under that curve. Right? And it would be, it would be 4 rectangles would give me some idea what the area would be. So by finding the sum of the areas of each rectangle, the area under the curve can be estimated. Well, you just take the same curve. Let's just bring it up. Okay, now we used 4 rectangles. You saw the area that was missed between the curve and each rectangle. All right, now let's try. Now 4 rectangles is good. What about 9 rectangles? Okay, as the number of these rectangles increase, now notice the area between the curve and the rectangle. These little areas are getting smaller and smaller now. So if I use 9 rectangles, okay, the area between the curve and the rectangle, these little triangular areas get smaller. So 9 rectangles would actually give me an area under the curve that would actually be more accurate. Right? It would be a better estimate than using 4 rectangles. So the point I want to get across here in calculus, if 9 rectangles is better than 4 rectangles, 90 rectangles would be better than 9. 900 rectangles would be better than 100. So it would be, so the more rectangles we have, the more accurate the area under the curve can be estimated. So what calculus does, when we do area under curve, so the rectangles become smaller, the amount of area missed by the rectangles decreases. Now, so the more rectangles you have, the smaller the amount of area missed by the rectangles. And we say the area under the curve, or area under a curve equals the limit of the sum of the areas of the rectangles. As the number of the rectangles approach infinity. So what calculus does is the number of these rectangles approaches infinity, that will give us the area under the curve from A to B. So like I said, 4 rectangles gives me an estimate. 9 rectangles gives me a better estimate. So calculus will find the limit as the number of rectangles approaches infinity, and then that will give me the actual area under the curve. Like I said, prior to the development of calculus, that was kind of difficult to do. Right. I believe this is going to finish up our introduction. So we'll stop here, and we'll start the next video in just a minute.